It's a double. Yeah. Just your voice. But I want to go. Yeah. No.
Didn't see me doing it.
So I just have to set and then we get back to see. Or things. That's it is, but. I don't. I think it's fine. It's for actually you go back. Follow that one. Okay.
All right, everybody, it is about that time. So 2, 4, 6, 8, 9, 10, 12, 15, all right? Release the breakers. Okay. So this morning we are going to deal with thermodynamics. This is the targeted learning method. So that's well, yeah. It's an exercise that, to be honest, is quite straightforward. Just takes a little bit of time. Like you go through plotting, calculations, then you write a short report. What I've given you here is a color printout of the full thermodiagram. I'm going to go through this step by step this morning. I've given you the data. I think it probably would be worthwhile. Let's see how we do. I think the way to move forward with this is for me to explain things as we move through, but I'd like you to actually plot this data as we go through it. So I'll walk you through how to do this. So it'll be a good practice exercise for the thermodiagram. What I've done online on D2L, I've uploaded. I originally uploaded the take-home exercise that's been replaced now with the updated one. Right? So there's the take-home exercise. There's a PDF of the color version of the thermodiagram that you have. And then there's also a PDF. It's a 14-page document that gives you all the background information that you need. Right? It may look a little overwhelming, but it walks you through it, and it would be, I hope, a useful frame of reference once you've plotted your diagram. That if you need a little bit of help and go, okay, I quite remember what this is. Everything that you need is in here. Okay, so I've done this a few times in the past, and students have generally done very, very well on this. So again, just being honest, if you're willing to put the time in and get this done, it'll be a good opportunity to move your grade towards the left of the distribution, i.e. towards the P's and the A's rather than the other way. So that's the plan for this morning. Okay. Just before we get going, let me just show you the surface analysis this morning, and then I do want to show you the current vertical sounding or thermodiagram for this morning, and then we'll get started. So here's the surface analysis, right? This is 6 a.m. this morning, and you can see the Metroplex has all these horizontal lines, and that is fog, right? There's a fog advisory out this morning. See, the reason why there's a fog advisory is the relationship between the dew point and the temperature, right? 57, 57, 50, 51, 49, 56, 56. You went onto your weather app, you would find that the relative humidities are all at what? About. Your dew point is 57 and your temperature is 57. Sense, right? That's why there's a fog advisory out this morning. For this analysis for this morning, there's just a lot of available moisture out there. You can see when you look at the Gulf of Mexico, just follow the Texas coast again, all of that flow is out of the south to southeast. This is classic setup in the early spring as the subsolar point begins to move now northward into the northern hemisphere. So right now, next week, what is it, 21st, 22nd of March, that subsolar point will be at the equator. Now it starts moving towards 23.5 degrees north. So that opens up the Gulf of Mexico. There's a stationary front here, so the area is, it's essentially pretty still, right? Look at the wind speeds here are all in the 5 knots, no wind, 5 knots. So the wind is fairly still, pretty stagnant. Although south of the stationary front, it's all coming out of the south and the southeast, as you'd expect. When you look at the vertical sounding here, so let's just look at the live vertical sounding. Where did that go? Yeah, here it is here. So actually, let me just go to the website here so you can see where I've gotten these from. So at the University of Wyoming has several places here, but I like this. It's an easy one to go to. It has all the stations around the US, and you can click on any of those stations and it pulls up the vertical sounding. Just as a frame of reference here, when you look at the top, the type of plot, okay, there's different things here. There's all the information, but the two that are most widely used are what is known as the skew T diagram. Let's just look at Fort Worth. Is that going to? So the skew T diagram is a vertical sounding, but it looks a little different than the one that you have, right? And part of the difference here is that you can see some of the lines slope up to the right here, the right 80 of that. It's a skewed diagram. I personally don't like them. They just skew my brain. I can't get my head around why they. And there's a reason why they actually use the skew T diagram, and it's that certain things plot more easily. So I wanted to just make mention of that in case you ended up going to the site.
we won't be using SKU-Ts. We will be using what you're using, and that is, I'm just going to use the PDF. That's known as the STUVE diagram, STUVE, right? That's the vertical sounding that you will use. So this looks, now what you have in front of you looks very familiar. We've got the mandatory pressure levels. Okay, and I'm going to walk you through all these lines in a bit more detail. But I just wanted to show you the temperature and the dew point plot this morning. So this is valid as it should be. Yeah, so this is 6. So this is 6 p.m. last night. Okay, they haven't got the latest sounding up this morning. So what we've got is temperature here and dew point here. So this is 6 p.m. last night, and you only have to go up here when you come across to this level. To that one there is right at about 300 meters. So at 300 meters, the dew point and the temperature join. Everybody see that, right? So there is the lifting condensation level, right? And then the temperature and the dew point are right on top of one another here, all the way up. The little deviation there, but all of this, right, is 100% saturated air. So there's a lot of moisture out there, and in fact, I wish they had the 6 a.m. one, because you would see that is an even deeper layer of moisture. So generally speaking, when we look at the relationship between temperature and dew point on this plot, it drops here. There's a drier cluster of air somewhere between 650 to 450 millibars, so about 4.5 to 6.5 kilometers up. The air is drier, but we do have this deep layer of moist air and it's my ability of what they are. So that's sort of the sort of makes sense. All right, David, I need to give you a couple of handouts. Okay, so that's the diagram that we're going to look at. Let's get going. Thermodiagrams. Let me just flip over here to the PowerPoint. Come on. Okay. So I'll move on from that one because I showed you the live one. Okay. So what I'm going to do here is go through the step by step as to exactly what these lines are. I'll build them in one by one. And then eventually you'll have the diagram that you have in front of you. Then I'd like you to plot this data. We need to plot it relatively quickly, so I'll walk you through that. Okay. So this is the standard thermodiagram, STUVE diagram, STUVE. And what we've got here is temperature on the bottom axis in degrees Celsius. Okay. And on the vertical axis, we've got pressure in kilopascals. Just add a 0 to that if you want millibars. Right? So these are the mandatory pressure levels. So that's 1,000 millibars or 100, 650 millibars, right? That's 500 millibars. That's the surface. So you can see these go in slightly different grades, right? 50, 52, 54, 56, 58, 60. Okay, 90, 92, 94, 96, 98, 100. So the horizontal yellow lines here are the mandatory pressure levels. That makes sense? That's the horizontal lines, the mandatory pressure levels. And these vertical ones come straight down here into the temperatures every 1 degree Celsius. We all work in Celsius here, even in the US, the thermodiagrams are Celsius computations. Okay, so that's the starting point. And then you can see the green lines are labeled, right? These are the dry adiabats. Okay, and the dry adiabats are for unsaturated air at 1 degree Celsius to 100. Right? So this is the 50 degrees Celsius dry adiabat, right? The 40, the 30, 20, the 10, the 0. You can see it reaches 0 here. They slope up to the left, and they're sloping up at that gradient of 1 degree Celsius per 100 meters. Remember, that's non-negotiable for dry air. Right? Please, as I go through this, folks, throw your hand up if there's something that doesn't make sense. Let's not get too deep into it if you're starting to get bamboozled. I want to make sure the goal absolutely is at the end of this that everybody's on the same page. It's exactly what we're looking at. So we've got mandatory pressure, vertical temperatures, and dry adiabats. Okay. All right, cool. And we've got the purple lines, which are the saturated adiabats. You can see I've labeled them here as moist adiabats. So here's the 50, the 40, the 30, the 20, and so on, right? Those are the moist adiabatic lapse rate. And those are variable, and so so it's a little tricky to draw true moist adiabats. So they've drawn these moist adiabats at the average rate of about 0.6 degrees Celsius per 100. Remember that moist adiabatic lapse rate does vary depending on how much moisture is out there. But these all work pretty well. Okay, so those are the moists. Well, good. Okay, cool. All right. Then you've got these very light blue ones, okay, and they relate to the top axis across the top here. And these are the mixing ratio lines, right? So the unit there is grams per kilogram. Right? That is the specific humidity. Remember when we talked about humidity, we can measure it in terms of relative humidity, we can measure it in terms of vapor pressure, we can measure it in terms of the absolute humidity or specific humidity. Here we're doing the specific humidity in terms of grams of moisture per kilogram of dry air. So let's just look at this one here, right under the caption, that's 10, okay? The 10 line here, this light dashed line, comes down. I know it starts getting very messy, right? That comes down at that angle. Don't read anything off this bottom axis, that all relates to the top axis, right? That is the mixing ratio. So every point along that line has 10 grams of moisture per kilogram of dry air. I'm grabbing please. Okay. Now notice that that scale is not uniform as you move from left to right across the top, right? We've got 0.1, 0.15, 0.2, 0.3, 0.4, so on. And then we start going 10, 50, 20, 30, 40, 60, 80 to 100. Okay. Why does that scale look like that? Because remember when we looked at the saturation vapor pressure, so this is vapor pressure against temperature, it does that, remember? So at these cold temperatures, the amount of water vapor in the air, the amount of moisture in the air starts increasing very slowly. And then as you start increasing temperature, it goes up in that curved line. Does that make sense? So that increase in the curved line represents the greatest spacing here in the lines, right? So the data that you'll plot on the take-home exercise won't necessarily be exactly on these lines. So you have to interpolate between them, right? So if, in other words, what I'm saying is if your data point lies right there, okay, and you're looking at these moisture lines, the mixing ratio lines, that's 40, that's 60, 50 would be there. You have to estimate that that's probably 43, 44, something like that. It doesn't have to be perfect, but you have to interpolate and estimate what that is, right? If you're interpolating down here, it's much easier. That's 0.1, that's 0.15. It's a much more narrow range. Does that make sense? Everybody good with that? So just be aware that as you move right across this diagram, the mixing ratios increase pretty quickly, and you just got to interpolate a bit more carefully. All good. Okay, cool. Something else on here. Why not just keep adding? So this is the final thing on here. And these are the height lines, right? So this is just height in kilometers. So these are the light gray ones that are sloping like that. So this is 7 kilometers, 6, 5, 4, 3, and so on. And that's the full thermo. Yep, that's the full. That's the full thermodiagram, STU diagram. So there's a lot of stuff on here. You've got the amount of moisture on the mixing ratio lines, you've got the dry adiabats, the wet adiabats, you've got the elevations, the mandatory pressure levels, you've got temperatures, and it's all in one block. Questions? All good. Okay. Yep. And I think what I'll do, if I remember correctly, I put the color one up on D12. I'm also going to put a lightly shaded gray, black, and white one that may plot a little easier for your exercise. All right.
Might sound silly, but public age.
A what? I don't in the PowerPoint, but we can quickly scribble one down. I'll tell you what, let me as I get you plotting here, I'll scribble one up on the board. Yeah. Okay. So that's the complicated part of it. Here's the simplified part of it. And this is what I've given you in the handout. Okay. This is all the data that you will plot in class. The take-home exercise, I've spread this out a little more and there's a bit more resolution. Right? So this is just a practice one. The one you're going to do for your grade is a bit more complicated. Complicated only in the sense that there's more data to plot and it's a little bit more nuanced. Right? So here what we've got is a vertical plot from 20 kilopascals, that's 200 millibars, down to 100 millibars. So the mandatory pressure, and the weather balloon has come back with the data, right? Surface temperature is 40 degrees, dew point is 25, at 90 it's 25, 20, at 80 it's 25, and 5. That's all you have, okay? So I would recommend that you get out your thermodiagram and you plot that data, okay? And what I think you should do, and so this is relatively standard. If you don't have colored pens and pencils, don't panic. But when you do this in your exercise, I would. So the standard is when you're plotting temperature is to use a red circle. When you're plotting your dew point is to use a blue X. So that would be dew point, right? So let me give you a hint as to how we'll start. I'm trying to work through this pretty quickly. It's fairly straightforward. I'll go back here, right? So your first data point is the temperature of 40 degrees and a dew point of 25 degrees at 100 kilopascals, right? So you just go to your thermodiagram and there's your temperature of 40 degrees, right? And you would plot your dew point at 25 degrees. And just plot that data. I want you to work through that, struggle through that for a little bit. Then I'll show you what it looks like. So work through that. You're just plotting temperature against pressure lines. I'll go back one and see if I can quickly come up with a legend here. Okay. Color one here. And purple. So your first two data points should look something like that. And so 100 millibars is 40, and 90 millibars, 90 kilopascals right here, is 25. Just right that like that. So good. Good. Color pens. I was supposed to take some energy focus to get worried on the bottom. This is your third data point. Then anybody struggling to orient where the data points are on that thermodiagram? It is a busy diagram. But yeah, 20 kilopascals is the one right at the top. That label below.
dew points for.
What did it do? Yeah, so do the dew point and. Yeah. Your temperature plot, I'm not going to rush you, we'll work through this. Your temperature plot should look something like that. Okay. Five to the Pascal here is 10. 10 and 13 and so on. And then it would be good. You just join up your data. Sign your iPhone and you don't have a ruler, roughly speaking, to the. And walk you through. First couple of viewpoints that I'm throwing on the pictures or something like that. Yeah, the viewpoint's going to be the same level. Viewpoint should look something like that. Yes. Maybe like that. So just a suggestion here, when you are doing this for your take-home exercise, I would do it in pencil first. What's really important is you can do a practice one in pencil. You can bring the thermodiagram into PowerPoint and you can actually do it, or you can do it in a graphic design, whatever. The key thing is to do it neatly, right? Because if you've got, that's absolutely fine now if your lines are wavy, if you're not using, there are no issues there. Final one needs to be as clean as you can. Okay, so if you haven't finished, that's okay. Just wrap that up and I'll start walking through the next set of things. So that's all the data that you need, right? That's all the data that you will have. You'll have a few more layers in the take-home exercise, but that gives you the vertical sounding, right? It gives you the actual temperature and the dew point, right? Okay, now the question is, how do we begin to look at that sounding and unpack the stability of the atmosphere? Because this is what the balloon sent back. Now we've got to start thinking about, okay, will this atmosphere suppress vertical motion, enhance vertical motion? How does that all work? Notice that, and so this is an important couple of points. This is an important point. So this first line that I've drawn on here, if you start at the dew point, right? And if you were to draw from the dew point, that first dew point at the surface, 25 degrees Celsius, and you draw a line that is at the same slope as the mixing ratio, right? Because at the dew point here at 25, if you draw a line, it doesn't fall right on this dash line, but it falls just to the right of it. And if you were to draw a line that more or less mimics that, see that goes right up to the top there, right? That gives you the absolute amount of moisture in the atmosphere at the surface at that dew point. Okay, so what I mean by that is, here's the dew point at 25, right at the bottom there. I've drawn that line that mimics that vertical mixing ratio, and so the actual mixing ratio here is about, I would accept, probably 21 or 22 grams per kilogram. Okay, does that make sense? Right, that's the absolute amount of moisture in that air right at the surface. Everybody needs to see that.
I know we're starting, now we're going to start moving quickly between temperatures and pressures, saturated adiabatic, mixing ratios, so, okay? Then,
Why did you go from this point up to the action?
I'm about to, good question. If we go from the actual, right, so here's your temperature right at the surface, or at 100 millibars, and you do the same thing, and you draw that line that sort of mimics the slopes here, you get to the top up here, and you're somewhere in the region of 52, 53, 54, 55 grams per kilogram. Okay? So what's the difference? The difference is, this is the actual amount of moisture in the air at the surface, 21 grams per kilogram. This is how much there could be if the surface was saturated. Does that make sense? Because if the surface was saturated, then where would the dew point be? It would be across here at 40. Is that feasible? No. Because a dew point of 40 degrees Celsius would be like 110 degrees Fahrenheit dew point. We know that physically can't happen, right? So what I'm doing here, let me just pull up, well, scribble this real quick. Okay, what I'm saying here is your vapor pressure, here's your temperature, there's the curve, so you're very familiar with that by now. Okay, and what we're doing here is we're saying here's the temperature at 40, here's the dew point at 25. Okay. That's where the air parcel is on that vapor pressure curve at the surface. Does that make sense? Right? So the 21 grams per kilogram, here it's in vapor pressure. We could change that axis and say, we're not looking at vapor pressure. Let's express this in grams per kilogram as the mixing ratio. Exactly the same thing, right? This here would be 21 grams per kilogram. That's how much moisture is at the surface in the air. How much can it hold? 55, something like that. Okay, cool. I see some nodding heads. That's good. Right. So when you draw those mixing ratio lines through the dew point, that's how much moisture there truly is at the surface. That's how much they can. Everybody good? Okay, sweet. All right. Now what do we want to do? Now we want to start seeing, well, what will happen if I start lifting this parcel? Or will this parcel at the surface lift on its own accord? Okay. So what happens? So I'll just scribble this up on the right here. So the mixing ratio, right? The mixing ratio at a dew point of 25, and you follow that line that I drew up there, right? The mixing ratio at the dew point is 21 grams per kilogram. Okay, the mixing ratio at the surface here, if you draw that line and go all the way up to the top here, I said 55, it ends up exactly at about 52, but 53 is okay. So the mixing ratio at the dew point is 21 grams per kilogram. The mixing ratio at the surface in the actual air parcel that David was asking about is 52 kilograms. So the relative humidity is 40.4%. Right here, the dew point and the temperature are far apart. All good? Okay, cool. Now let's try and figure out where the lifting condensation level is. That's the next key thing we look at. Where's the lifting condensation level? So how do we do that, right? So the lifting condensation level, we go back to the surface here. Here's the surface air parcel. Here's the actual air parcel's temperature, right? So the two green dots I've put on here is let's start at the surface. Okay. So how am I going to determine where the lifting condensation level is on this diagram? Standing at the surface, got my parcel of air. The moment it's come back and said it's 40 degrees Celsius, pretty quirky, right? Dew point says it's 25. Okay. Is that air saturated at the surface? Got a relative humidity of 40.4%. So as I try and lift that parcel to see if it's going to rise on its own accord, what rate does it cool at? 1 degree Celsius per 100 feet. Going to cool at the dry adiabatic lapse rate. If these two dots were sitting on top of one another, which they physically couldn't be, because if they were, then they would be up here and the dew point would be 110 Fahrenheit. Remember that little question in the exam? But if they were, then that rising parcel of air would just simply start cooling at the saturated adiabatic lapse rate, right? In your diagram, was it green? Yeah, no, purple. I think they are on your diagram. That's a bad legend. Sorry about the crappy legend. But they're not sitting on top of one another. So how does this work? Okay, so you try and lift the parcel here at the surface. You know it's going to cool at the dry adiabatic lapse rate. So what do? You draw a line right here that follows the dry adiabatic lapse rate. There it goes. Boom. You can see that? Okay, go back. You just follow the dry adiabatic lapse rate. So that's the slope at which the parcel will cool because it's unsaturated. But where does the lifting condensation level come? How does the lifting condensation level? What you do is you go to the dew point. Okay, you start at the dew point and you just go up that mixing ratio line. You just follow the actual amount of moisture in that mixing ratio line. So you start here and you just lift it following that 21 grams per kilogram line. Okay. What I found in the past is that that's a bit of a stumbling block for most people. Right? It's a bit confusing. So we're at the surface, we know the parcel is pretty dry, relative humidity of 40%. Now you want to lift it. You're going to lift and cool it dry adiabatic lapse rate. Okay. Right. But we're going to make the assumption that the total amount of moisture in that parcel is conserved. Right? It doesn't change. So the total amount of moisture at the surface here, in terms of how many grams per kilogram, as we lift that, we're not going to start losing moisture to the side of the parcel. Right? We're going to say that 21 grams per kilogram is going to stay within my parcel. You have to make that assumption to determine the stability. All right. So all you do here, I'll just go back a second. So all you do is you lift the parcel at the actual temperature along the dry adiabatic lapse rate, and you lift the dew point and you just follow the same slope as the mixing ratio. And where those two intersect, the zinc. That's the lifting condensation. All right. So here comes the dry adiabatic lapse rate. Here comes the mixing ratio there, and where those two intersect is right there at the green line. So you can draw that on your diagram. Okay. Just you can use a ruler or a pen. Just take the slope from the surface and then the slope at the angle that more or less mimics the mixing ratio line. And throw your hand up if you need a little nudge or help. So it's kind of cool that, and I did this specifically, that the data point is 40 degrees Celsius, because 40 degrees Celsius lies right on the dry adiabat, and you don't have to interpolate anything. So you know you just follow that dry adiabat, and then you draw in very light pencil just from that dew point, mimic the dashed line until those two meet. Right there. That's the LCL. Does that make sense to everybody? I know you have to make this assumption that seems wacky, that we're not losing or adding moisture, which of course does happen in reality. We have to work with the parcels to determine stability. Everything good. All good. Sort of. Everybody got the lifting condensation? Okay. So at what height does the lifting condensation level occur? Now we're going to use the right hand. What's the height of the lifting condensation level? Ish. Okay. It's like 2 kilometers. 2-ish. Okay. Right at 2, just slightly, maybe just slightly below 2, just depends on how accurate you've been, right? So here's a nifty little equation. I'm just going to put this down on the right. If you want to get a really good estimate of the lifting condensation level, the lifting condensation level, okay, you can calculate the height by taking A. Well, what's A, right? A is a constant, 0.125 kilometers per degree Celsius. And you take A multiplied by, and you just take the temperature minus the dew point. That's a nifty little cheat that gets you the lifting condensation level. In reality, that would be probably within a few tens of feet, right? So what's the temperature? 40 degrees. What's the dew point? 25. Okay. I'm not a great mathematician, but 40 minus 25, I think, is 15. 15 multiplied by 0.125, that gives you the lifting condensation level at 1.875 kilometers. So you're spot on, Jackson. I would accept that. If you'd answered 2, you're good. You're within 120 meters of the lifting condensation. Just as a little thing in your pocket when you're doing, you can do that. When you do the take home exercise. All good. Please do not hesitate to go. I am not good. Okay, all good. Everybody good. That's awesome. You are. Okay, now the question is, so that's the lifting condensation level. So you also get to its lifting condensation level in this scenario. Ooh. Would that, you just said the parcel should rise and cool at the dry adiabatic lapse rate, and if we just follow the mixing ratio, it gets to 1.875. Would it get there, David? You're nodding left and right. You say no. Why? You're correct.
Or to reach the lifting concentration level, it has to be fully, like 100% saturated. It's like when we go on the saturated vapor curve, it meets there and then excess moisture.
Correct. Yeah, but take one step back from that. All I'm asking is whether it's saturated or not, will that parcel of air get to the lifting condensation level? Not. Is there anything that looks like it's blocking the way? Or let me rephrase that. If that's the lifting condensation level, and I shout it out to you, David, okay, release the balloon, please. Would it start rising? From a stability perspective? Absolutely, it would start rising. Right? It would rise at the dry adiabatic lapse rate. Rise at that dry adiabatic lapse rate that you've drawn in. And the temperature of the parcel at any elevation here, look at 1 kilometer, the temperature in the parcel is that. The temperature of the environment is that. Now you've got to start comparing the temperature in the parcel to the temperature in the environment. In the lower layers here, the temperature in your parcel that you are lifting here is always warmer than the surrounding environment. So it'll continue to rise until it gets there, where the temperature in the parcel is now the same as the environment, and it'll stop. It won't rise any further. Does that make sense to everybody? Now the stability conversation comes in. If you took your hands off the parcel, where's it going to go? It's only going to go to this point, and it'll be a neutral atmosphere. It'll stay right there. It's not going to get to its lifting condensation level, even though the lifting condensation level is whistling from the other side of the environmental lapse rate. Yo, come over here. Let's come a little further to the left. It's not going to get there. Now, this is the lifting condensation level for the entire atmosphere. Yeah, good questions. Right? Okay. All right, cool. So it won't reach the lifting condensation level. But that's where the lifting condensation level is. So now we can start saying, well, what's going on at the lifting condensation level? So at the lifting condensation level, right, you would say, well, what is the temperature? So if this here is the lifting condensation level, what is the temperature? Well, you can just go down to the axis and say the temperature is 22 degrees Celsius at the lifting condensation level, right? The R at the lifting condensation level, the R, the mixing ratio, the amount of moisture hasn't changed. At 21 grams per kilogram is going to stay in that parcel, right? So the R is 21 grams per kilogram, right at that lifting condensation level. But if you could get it to the lifting condensation level, let's say you just went, you know what, I'm going to keep dragging that parcel of air up, and I'm going to get to the lifting condensation level. What happens? If you could get that air parcel to the lifting condensation level, what's the relative humidity of the lifting condensation? 100%. Right? The temperature's reached the dew point. And if it wanted to keep rising, what rate would it cool at? It would cool at the saturated adiabatic lapse rate, right? It would cool at the saturated adiabatic lapse rate. But if that parcel kept rising, and in fact, it would now start rising following the saturated curve, right, which is that totally curve in your diagram. And so here is the most complicated part of this diagram. You're at the lifting condensation level, right? It's not going to get there because it's not going to punch through this part here, but let's assume it did. let's assume you have the lifting condensation level here and you're saying, okay, now start rising and you start rising at the saturated adiabatic lapse rate at 0.6 degrees. You start following that more gentle curve, right, as it goes up. As that air parcel goes up, wherever it goes in this atmosphere, please always assume that the amount of moisture is conserved, right? That amount of moisture is conserved. 21 grams per kilogram, 21 grams per kilogram, 21 grams per kilogram. Right? You're not adding moisture from the outside. You don't have a vacuum cleaner sucking air in or pushing it out, right? That is a really key assumption. So your big balloon, if you're now at the lifting condensation level and saying, okay, I'm still going to drag you up and you're going to cool at the saturated rate, the amount of vapor is conserved there. The red dot, let's go back a second, this red dot is now going to rise and cool following the saturated adiabatic lapse. Okay, and you've got to interpolate, you've got to guesstimate because it's a curve. Does that make sense? Okay, cool. So let's say, and so here's the sort of end point of the, hopefully the confusion, then we'll put this all together, right? Let's say your parcel, I'll just go back here, let's say your parcel gets to the lifting condensation level and rises and cools at the saturated rate and gets to a pressure of 40 kilopascals, 400 millibars, or an elevation of about 8.5 kilometers, right? So now it's up at 8.5 kilometers. It's sitting over here, okay? It has cooled, just come all the way down to the temperature here. It's cooled to below freezing. Gone up through the atmosphere, it's cooled to below freezing, right? But the total amount of moisture in that air parcel has stayed the same. Okay, it stayed the same along that 21 grams per kilogram of mixing ratio, right? Here, this data point right here is sitting on a mixing ratio line of 8. Right, so your air parcel is now at 40 kilopascals at 400 millibars, it's 8.5 kilometers. Now the air parcel is sitting on a mixing ratio of 8. But I told you that the total amount of water is at 21 grams per kilogram. Ooh, that air parcel has now got 8 grams per kilogram of moisture. But where's the 21 coming from? What's the difference in, what's that blue line there? I'll explain what RL is in a second. You can think of the saturation vapor pressure curve. Okay, your air parcel is here, 21 degrees, 21 grams per kilogram. At the lifting condensation level, it's 21 grams per kilogram. Relative humidity is 100%. Now you've lifted it up. It's slid down the curve here. It's cooled to less than 0 degrees. The vapor pressure here, expressed in grams per kilogram, is 8.
Didn't get that. Could you try again?
I am definitely getting one.
Is it the, we talked about earlier, the axis usually works
As heat and, what do you see?
and
Yeah, exactly. The 21 grams per kilogram here is at the lifting condensation level. The 21 grams per kilogram here is still there at 8.5 kilometers, right? The 8 grams is the amount of water vapor. 21 minus 8, 13 grams is liquid water, cloud. That's the key, right? So RL is the liquid mixing ratio. You started here with 21 grams per kilogram at the surface. Did you see clouds? No, you didn't see any clouds because the relative humidity was 40%. You get to the base of the lifting condensation level and the bubble goes, yep, still got 21 grams per kilograms, folks. Okay, cool. Now I'm at the base of the clouds. We get to 8.5 kilometers up and that bubble says, I've still got 21 grams per kilogram, except now 13 of that you see as liquid water as cloud, 8 grams per kilogram is water vapor. Does that make sense? It's a really safe assumption to assume that as that air parcel goes up, it's carried all of the liquid water
and the water vapor. Remember the size of a water molecule, right? Tiny, the size of a cloud drop, 5 to 10 microns. It's going to take nothing to lift that all up. So all of that moisture, it's safe to assume, will be carried vertically up. The problem is once it gets to the lifting condensation level, it starts shedding that as liquid water, RL, the liquid mixing ratio. Everybody good?
So it's mixing ratio of the 13.
Yep, we're doing. The liquid mixing ratio is the 13. What's the 8? The vapor mixing ratio. What's the 21? The total mixing ratio.
Where did the red dot? Is that just like another,
This one here,
the one that you used, yeah, that one's just like if it was.
that's your hypothetical lifting. From the lifting condensation, I could probably do that in a different color. That's from the lifting condensation level, let's cool at the saturated adiabatic flux rate.
If our current red line had a dot there, that's.
Questions? Okay, I think that's the most complicated part of the diagram, is that all along that S-end, you're assuming that the amount of moisture in that parcel is going to stay the same, 21 grams per kilogram. Now it's just a question of, does it reach the saturation vapor pressure curve? If it did, it would be the lifting condensation level. Anything above that would be squeezed out as liquid water. Okay. Next, now we've got to try and determine what layers are stable. So this is easy. Okay, and then we'll draw the whole diagram. All right, so that's a little bit of hypotheticals. We've got our temperature, we've got our dew point, we know where the lifting condensation level should be, right? We know that the parcel is probably not going to get there because it gets blocked by that, not an inversion, but an isothermal layer. We know that the total amount of moisture carried up vertically will stay the same, right? Now let's determine stability layer. So the stability layers is easy, right? You don't really have to do this in any detail now. All you do is you go to each of your red dots and you draw a line at the slope of the dry adiabatic. That's all you do, right? So you go to the red dot, draw a line at the slope of the adiabatic fashion, right? So we know that that one is following the dry adiabat here, slope of the dry adiabat there, slope there. I should have done this different color, but there it is. All you're doing is you're going to each dot, each layer. You're trying to determine the layer stability. So you go to each dot and say, if my parcel was here and it started lifting and was unsaturated, it would cool at the dry rate. Okay, at that particular layer in the atmosphere. So you're sort of looking up and down in the atmosphere and trying to determine what layers are stable or not. Does that make sense to everybody? So you can just look here. What's this lower layer here? This lower layer up to the point where it joins there, that layer there is clearly unstable, right? Because why? Because the temperature along your dry adiabat is warmer than the environment. All you're doing now is you're comparing the temperature along the dry adiabat to the temperature along the environment. And all of these layers, this one here, where the temperature shoots off to the left here along the dry adiabat, is colder than the environment. So anytime that line or arrow goes left and lies to the left or below the dry adiabat, that's all stable. There's one layer here, which is, it's almost right on it. You could probably argue that that's a neutral atmosphere, but I would probably put neutral in there and the rest is all stable in terms of layers, right? So this is unstable here through to where your parcel bumps up against the environmental lapse rate, right? The next layer is totally stable because at each point there, if you start your parcel, it's going to be to the left or colder than the environmental lapse rate. That makes sense to everybody? Okay, cool. All right. So I've just drawn in two little hashtags here on the diagram. This is the key one here, right? There's a little cap here. It's not an inversion, but there's a little cap. So if I go back a second, we're saying that this is unstable up to here. Then we've got this little cap in there that's blocking things in the atmosphere. In the take-home exercise, I'm going to give you an obvious one. It's going to be a new one, right? BLU stands for boundary layer. Don't worry about it. That's just the boundary layer. Okay. So let's now draw the full parcel, right? Now we're going to get to the point of
is this whole atmosphere stable or unstable? What are we looking at in terms of the potential for thunderstorms and severe thunderstorm development? So you come back and you draw your line from 40 degrees along the dry adiabat. You draw your blue line up to the lifting condensation level, and then at the lifting condensation level, if it reaches the lifting condensation level, you draw that line at the saturated adiabatic pressure. That's what I want you to do on your diagram before going. Right, that's the key one right now. So that's the explanation of the layers. So if you just go and you probably already got this, right? So just draw your line, you can take your, if you're drawing your lifting condensation level, you can just go from there. Draw in this dashed line from the lifting condensation level and just mimic as best you can the dot here from the lifting condensation level. Just draw that dashed line that mimics the saturated adiabatic pressure. And then once you've got that in there, we can take it. So does that make sense? Yeah, that's perfect there. Right along that dashed line. Why not? Perfect. Cool, cool, cool. Because that's what you see on all the vertical soundings. We have time, we'll go back and look at the vertical soundings. The vertical sounding will be the temperature line, you form that, the dew point, you form that, and then it'll be the hypothetical path along the dry adiabatic, medium lifting condensation level, and up and beyond that. All good, all good, good, British. Okay. Sweet. Okay. So now we've got the vertical sounding and we've got this full saturated curve all the way up. Okay. So just a couple of things to point out here. So this here is the LCL, right? You've got that on your diagram. Okay, so that's all good. Okay. We know that the parcel is not going to be here. We know it's going to stop here at the cap because there is the neutral atmosphere. So that's the lifting condensation level. What is this line where your sounding crosses over the environmental latitude? That's a hugely, that's the most important point on the diagram. That right there, come back to that. This point here, where that air parcel from the LCL crosses over the environmental latitude. That point there is known as the LFC, like a pop, like the level of free convection. The level of free convection. The level of free convection is the point where if you took your hands off your parcel, what would it do? It would now rise. If you took your hands off that parcel, it would rise. Why? Because now it's rising and cooling at the saturated rate, and all along the way here, the saturated rate in that parcel is that parcel's warmer than the environment, warmer than the environment, warmer than the environment. The greater that area, the more that divergence, okay, the faster that parcel will rise. But you have to get that parcel to the level of free convection. It's not going to get there in the current situation because we've got this cap that is keeping the air only rising to about 1.5 kilometers. It's got to get through this layer. We've got to go from this layer here to this layer here, where you can take your hands off the parcel and it will rise on its own. So that's the key point here, the level of free convection, the point at which the parcel inherently becomes unstable and will zip up through the atmosphere. Right? This little Zi, right, is what is known as convective inhibition. Convective inhibition. This point here is where any convection stops. So you take your hands off the parcel here, it's going to rise and cool at the dry rate. It's warmer than the environment, warmer than the environment. You said it's unstable, that's great. But it gets to this point here where it becomes neutral and the convection is stopped, right? It's inhibited, doesn't go any further. Cannot get to the lifting condensation level unless somehow it can punch through that little cap. Make sense? And then what we do is we'll shade in this little area. I've done it in orange here. We'll shade in this area from the convective inhibition, right, to the level of free convection. So that orange shaded area from here
from where it won't punch through that starting inversion here to the level of free convection. That's the shaded area is the amount of convective inhibition, right? Okay. We'll get to the end here, and then I'm going to reverse it and take questions and walk through some stuff, right? Sweet. The final part. So we call that SIP. Convective inhibition is the shaded area. Okay. So under this, so right at this condition, right at this stage, we've got a situation where we've got an unstable layer down here. Okay. The parcels are happy to go up and down here and rise, but they're not going to go through there because we've got this convective inhibition layer where it can't go through the environment. We've got a lifting condensation level that can't get there, right? We've got a level of free convection. This parcel of air can't get there. It doesn't go, whoop. There's no bypass here, right? This lid is acting as a lid right there. That was going on last Thursday, same deal, right? Why they were calling for severe thunderstorms and all those shenanigans. We had that inversion here that was keeping everything cooking. Okay. The question is, how do we get that parcel around this convective inhibition? If it was an inversion, which would be the strongest form of cap, you would see this, right? The temperature would do that, the parcel would have done that, and it might have done that, right? There was an inversion there, then this would be your convective inhibition. It would be much larger. An inversion, remember, is the most stable layer in the atmosphere. Okay? So how do we get around that convective inhibition? We can do a couple of things. Okay, you can heat the surface. Remember that afternoon heating. If you heat the surface, okay, you can begin to bypass the cap, but you got to heat it. So in other words, if we heated the surface from 40 degrees to 50 degrees Celsius, so that's about 125 to 130 Fahrenheit, that seems a little unrealistic. Okay. But if you could heat that surface and your parcel got here and it started rising and cooling at the dry adiabatic and rising and cooling and rising and cooling and rising and cooling, it might bypass that layer and get to the level of free convection, and then you'd be off to the races. Okay, does that make sense? So you can heat the surface. Afternoon heating will begin to erode the cap. But what's much easier is just to force it. Bring in a cold front. So you know what? We don't worry about this. We're going to just lift everything. That whole atmosphere, I don't care whether you're stable or not. Cold front's going to come in, all of that air lifts, and it gets to the level of free convection. And then you're off to the races. Final thing is this big shaded area between where the parcel should go along the saturated adiabatic lapse rate, right? In other words, from the level of free convection right here, and it follows up there to the actual environment. Okay, so this is really what forecasters look at when they're starting to look at predicting severe thunderstorms. Okay, the shaded area is known as K. Convective available potential energy. Convective, that's the physical overcurving. Convective available potential energy. In other words, whether this is stable or not, whether we've got a big inversion here or not, what is the potential for convection out there? Okay. And the bottom line, the bigger the shaded area, the more potential energy there is in the atmosphere. Okay. The bigger the shaded area, the greater the potential energy. And I'm going to get you to estimate convective available potential energy in the take-home exercise. This is the way in which you do it. It's actually pretty simple. It looks messy because now there's so many lines, right? But the convection available potential area is you count up the squares, okay? And you count up the squares that are defined as the width of the temperature and the height lines, right, are the squares. If this makes sense. So here's a square there. There's another square there, right? There's another square there. And remember, these are the height lines. So you're not counting up the squares based on the pressure. You're counting up the squares based on the height lines and the temperature. So the height lines are sloped
and the vertical temperatures. Okay, so here's one square, and you count up the number of boxes. Okay, so if I was to, so there's a box, and each box is 5 degrees Celsius wide. Okay, each box is 5 degrees Celsius wide by 1 kilometer high. That's what each box is on the diagram. Okay, and each box's area is 5 degrees Celsius kilometer. So that's simple and straightforward. You just count them up. There are the dots. Okay, I've counted up the number of boxes. Here's one, there's one, there's one. Now what do? You've got one here that's a half a box. Well, you kind of estimate. There's a half a box. There may be another half a box here. That's a whole box. You start estimating halves and quarters. But hopefully it's simple enough where you count up the number of boxes. So in this diagram here, if I was to count up all the boxes, there ends up being about 23.5 boxes. Okay, and 23.5 boxes times 5 degrees Celsius kilometers, 23.5 times 5, gives you the total convective available potential energy. And here's the reference table. We'll work with this one here. When we come back and look at numerical weather prediction, there's an equivalent case in terms of how many cubic meters per second squared, but don't worry about that right now. In other words, if you're coming out here, let's say you come out and you count up the number of boxes, and it looks like this. There's your curve, and let's say your temperature line looks like that. And there's almost no cape. There's no shaded area in here. Almost none. Maybe you count one box or two boxes or three boxes, right? If your cape ends up being less than 0, there's no convection. Right? If your cape is between, and you're not going to have to remember this, if your cape is less than 26, but greater than 0, in other words, if you've got just a few boxes, then you may see some cumulus clouds, right? But as soon as your cape starts getting greater than 66 or greater, then you start looking at, okay, wait a minute. Now we've got huge amounts of convective potential energy out there. It turns out in this situation, if we've got 23.5 boxes, times 5 is 117. That is down here in another whole column. Right now, we would be looking at real trouble, severe storms, and possibly tornado warnings for that situation. So the bottom line here, everybody, is that the greater the divergence between what the parcel is doing and what the temperature is doing, that gives you the greatest potential for convection. That's what you'll be doing in the take-home exercise, right? So 2 simple lines of data. Temperature plot and a dew point plot. You end up getting a whole bunch of stuff out in terms of looking next to it. So the main point is to plot your temperature and your dew point, right? Look your temperature along the dry adiabatic line. On the dew point, follow the mixing ratio curve, determine what your lifting condensation level is. And I'll ask you some questions on that, calculate what the relative humidity is at that point. That's easy. Right? Determine what layers are stable or not stable. Then from the lifting condensation level, draw your curve following the moist adiabatic pathway. Figure out where the level of free convection is. Okay. The LOC, I should have pointed that, that's at the top, that's the limit of convection. No air will rise above that. And then you calculate the cape, and then I'm going to say discuss. Right? What would you, as a weather forecaster, say about the atmosphere on that given day? Or potential for storms and so on. So 15 minutes. It's a lot to go through. Right.
Relabel them.
Yeah. I will go ahead. But I think that's written out in the document
And all those other numbers.
all those other numbers. Yeah. So you'll see it in the document the line that says once you've done that, please calculate these, determine these, now do this, now do that, produce the full thermodynamic.
So for this one, the cape was 17.
So from what's on the cape was 23.5 boxes, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we start adding up all these little halves. Ends up at about 23 boxes. You multiply that by the 5 degrees Celsius kilometer. So the total cape is 117.5, which is greater than 92. These are the boxes, degrees Celsius kilometer. If you were to calculate it using a little bit more complicated math, you would actually get the cape in energy potential.
Did you say that LOC was
Limit of convection. So that's where everything stops. Yeah.
are all, is everything the distance between the edge of the cave?
Say again?
Or like, whenever we were talking about like the clouds and what's liquid, would you just be able to see like our red dot and go to that line here?
Yeah, so you do that first, right? I'll say, okay, calculate what the liquid ratio is, what the vapor ratio is, what the total ratio is. So you do that before you do all this. Just go from the lifting condensation level, right? Lift your parcel of air, follow the saturated rate to a certain height, and then keep that mixing ratio at the same height, and then you start just simply reading up the lines. What that thing would be. Yeah. Probably thinking, was it diamond? But once you work through it, right away you get a chunk of grace. It'll take some time, right? Especially if you want to make it look good. Tell pretty quickly because that until May 3, whatever it's due. I don't remember last year. You at the end of the semester, more than happy to go through with it with you, sit down with you, go through it again. You know, if you get really lonely over spring break, view this video. So this is the one lecture that I recorded and I'll put it up there. Okay, questions? On the thermo diagram. Yep.
Explain that.
Yeah. So let me fly back there a second. Let's try and take all these off a second. So once you, okay, so we are looking at what layers are potentially stable and what layers are potentially unstable. The simplest way to do this is just to take your temperature data points and draw an imaginary line that follows the dry adiabatic line at each data point, right? So just take an arrow from the surface and follow the dry adiabatic line here, dry adiabatic line there, dry adiabatic line. Following these dry adiabatic slopes. Okay, and then all you do is you compare the temperature of your hypothetical parcel along that dry adiabatic to the temperature of the environment. Always do that, right? So if it's this layer over here, and you're following this line, the temperature here is always colder than the actual environment. Therefore, it's stable. Does that make sense? Yeah. I am going to give you, I have given you an interesting one. It's not going to be a simple, straightforward. Well, the whole layer is stable and there's no convective in it. It's quirky one. Good. What else? Young meteorologist. I would say no more than that. Yeah. Now, the write-up, take your time and look at it and say, you know, and there's a classic slattery at the end that says discuss. Right? So what is this? What is the sounding tell? What can you tell from this sound? In terms of stability, what is it likely to do? If you see that there's a big inversion there, you may want to say, well, if the inversion's there, and if this inversion was broken, then you would probably get strong vertical uplift because there's just so much cake, you know, that kind of thing. But no more. No thesis on discussion. I'm much more interested in, can you do the plotting? You will see a vertical sounding on the final exam in the assessment. I'm going to give you an interesting weather outbreak. Please don't spiral down and struggle with this. This is a great opportunity. It's historically, most people do it, do the discussion, let it. Yeah.
When finding the code, the difference between the temperature, how long it dry, that rate, and then.
So you did follow the consideration. Yeah. Don't take it from the, I've seen you do this, viewpoint, and then follow the saturated. You have to make that assumption that 21 grams per kilogram starting with the surface there all the way. Good. And you can do this on the front. Yeah. You'll do it with the plot. If you want to do the plot in hand by hand, that's cool.
and your written discussion. I've had some people that they do it on, you know, they do it on PowerPoint, whatever. Yeah. All right, any other questions? I'll hang around for 7 minutes. I'll see you on the other side. Be safe.
Feel like I see certain voice.
Good luck.
The Apple weather thing, like, I don't trust it. I haven't like, you're gonna have like 8 or
Yeah. There's plenty of moisture out there, that's for sure.
Yeah.
Yep, have a good one.
I like
Yeah, it's like.
No.
Yeah.
Yeah, give me 1 sec. Let me sign off here.